Hey everyone, welcome to this explainer where we're going to completely transform the way you look at chemistry. If you've ever stared blankly at that massive periodic table hanging on a classroom wall and just felt totally overwhelmed, trust me, you are not alone. But today, we're acting as your guide to mastering what is, without a doubt, the ultimate chemistry cheat sheet. And honestly, the best part? We're going to do the whole thing without relying on a single ounce of rote memorization. We are just going to decode the logic behind the map.
So, let me ask you something. Does the periodic table feel like just a chaotic, random list of elements that you somehow have to cram into your brain? Because yeah, it definitely looks pretty intimidating at first glance. But what if I told you it's not random at all? It's actually a highly structured code, literally just waiting for us to crack it.
Okay, let's dive right in. The modern periodic table isn't just alphabet soup. Far from being a random assortment of letters and numbers, this iconic chart is actually a beautifully organized geographic map. Every single element is placed exactly where it is for a very specific reason, and the whole thing is governed by just a tiny set of logical rules. Once you actually understand the underlying coordinate system, you can predict exactly how an element is going to behave just by looking up its zip code on this grid. So here's our roadmap for today. First, we'll decode the table's history. Then, we'll learn how to navigate the grid. Third, we'll uncover the rules of attraction. Fourth, we'll track the major periodic trends. And finally, we'll break down the great shift between metals and nonmetals.
All right, part 1, decoding the table, a brief history.
To really appreciate the genius of this map, we kind of need to see how early chemists slowly figured it out, because it definitely didn't happen overnight. Back in 1815, Dohrao tried grouping elements into triads, basically groups of 3 where the middle guy had the average atomic weight of the other 2. Kind of neat, but it didn't hold up for everything. Then in 1864, Newland tried octaves, noticing that properties repeated every 8th element, almost like notes in music. By 1869, Mendeleev gave us the first real periodic table, arranging things by increasing atomic weight. Better, but still flawed. It wasn't until 1912 that Henry Moseley had a massive aha moment. He discovered that the true key wasn't atomic weight at all, but the atomic number, the exact number of electrons or protons an element has. And honestly, that changed everything.
Moving to part 2, navigating the grid, groups and periods. Now that we have the modern setup ordered by atomic number, how do we actually read it? Well, the grid is built on just 2 simple directions. Horizontally, moving left to right, we have 7 rows, and these are called periods. When you move across a period, those elements all share the exact same number of electron shells. Vertically, going top to bottom, we have 18 columns, which are called groups. Moving down a group means those elements share the exact same number of valence electrons. Those electrons hanging out in the outermost shell. So the big takeaway here is this. Because elements in the same vertical group have identical outer shell configurations, their chemical properties are incredibly similar. They basically behave like a family.
Which brings us to part 3, the rules of attraction, or as I like to call them, the puppet masters.
Okay, so we've got our grid. Now, here's where it gets really fascinating. There are 2 invisible, competing forces that dictate literally every single trend on this entire board. Understand these 2 forces, and the whole thing just clicks open. The first puppet master is nuclear charge. This is the positive pulling force coming straight from the protons packed into the center of the atom, the nucleus. As the atomic number goes up, you're packing more protons in there, which means that positive charge gets a whole lot stronger. Think of it like a giant magnet. The stronger the magnet, the tighter it pulls those negative outer electrons inward toward the center.
But fighting against that magnet is our second puppet master, the number of shells. These are the physical layers of electrons orbiting the nucleus. While the nuclear charge is desperately trying to pull everything inward, adding more shells does the exact opposite. Every single time you add a new shell, you are physically increasing the distance from the center to the edge. It acts like a shield, pushing those outermost electrons further and further away from that magnetic pull.
Let's see this battle in action in part 4, major periodic trends, reading the weather. All right, we've got our grid, and we know our puppet masters, the inward pull of the nucleus versus the outward push of new layers. So how does this actually affect the elements as we travel across the map? Well, the best way to visualize this tug-of-war is through atomic size, which is exactly what it sounds like, the distance from the center to the outermost shell. Let's see how our puppet masters manipulate this. Picture moving across a period, from left to right. The number of shells isn't changing, but the atomic number is going up, which means that central magnet, the nuclear charge, is getting stronger and stronger. You've got a stronger magnet pulling on the exact same number of layers. The result? The whole atom gets yanked in tight,
and the atomic size decreases, shrinks right down. But go down a group, top to bottom, it's a different story. Yes, the magnet gets stronger, but you are piling on massive, brand new layers of electrons. That huge addition completely overrides the inward pull. The result? The atom swells up and the atomic size increases. So, left to right, they shrink. Top to bottom, they swell.
Armed with that visual of size, we can easily tackle what I call the energy and attraction trio. The source material throws three big terms at us: ionization potential, electron affinity, and electronegativity. I know, they sound incredibly heavy and academic, but if we just group them together as attraction metrics, they become so much easier to handle.
Let's break them down real quick. Ionization potential is simply the amount of effort it takes to steal or remove a loosely bound electron from an atom. Electron affinity is basically the flip side of that. It's the burst of energy released when an atom willingly grabs a new electron. And then electronegativity is just the atom's overall tendency to hog electrons in a chemical bond. Ultimately, all three of these are just different ways of measuring one simple thing: how badly does this atom want to hold on to electrons?
And this brilliantly ties right back to our atomic size. Think about it. When you move left to right, we know the atom shrinks. The nucleus is super close to the edge, holding on for dear life. Because the grip is so tight, it's really hard to steal an electron, and the atom is desperately hungry for more. Logically, all three of those attraction metrics shoot up. But go down a group, the atom becomes this massive, bulky thing. The outer electrons are so ridiculously far from the center that the atom barely even notices them. So obviously, all three attraction metrics sharply decrease.
Finally, part 5, metals versus nonmetals, the great shift.
So, how does all this invisible push and pull create actual physical stuff, like, say, a chunk of solid metal versus an invisible gas? Well, over on the left side of the table, we've got elements that are perfectly happy to just ditch their loose electrons. Those are our metals. But as we travel to the right, atoms shrink. Their magnetic grip gets crazy strong, and they transition from electron losers into desperate electron gainers, and those are our nonmetals. So metallic character, meaning how eager it is to lose an electron, drops off as you move right, while nonmetallic character shoots up. But what happens when you go down a vertical group? Remember, at the very bottom, atoms are absolute units. They're huge. Their outer shells are massive, meaning those edge electrons are super loose and practically falling off. Since metals are all about losing electrons, it totally makes sense that the elements at the very bottom left are the absolute most metallic, highly reactive elements in existence.
And boom, there you have it. You basically possess the master key now. You've completely decoded the matrix of the periodic table. Left to right, atoms shrink, and their attraction forces surge. Top to bottom, they expand, and their grip drops. The left side is ruled by electron-losing metals, and the right side is dominated by electron-hungry nonmetals. You literally don't have to memorize a thing anymore. You just read the map and follow the logic. So, I'm going to leave you with this one last thought. Imagine tomorrow scientists announce they've synthesized a totally brand new element, and it drops right into the very bottom right corner of the table. Based on everything we just covered, the puppet masters, the size, the grip, what do you think you could immediately predict about how that unknown building block would behave? Think about it. Thanks for hanging out with me for this explainer, and keep that curiosity alive.